So in the previous class we have discussed about the torsion equation, which was nothing but T by J is equal to tau by R is equal to G theta by L, and we have discussed about the various terms or the nature of the terms that we use in the torsion equation. Now let us discuss about the torsional rigidity. So torsional rigidity is nothing but the torque required to produce a unit twist, twist, twist in the shaft of a unit length. So if you take the first and last terms, because you can expect a question with all these terms, because all these terms are measurable. So the problems that comes under the torsion can be with any variables. It's not like what we solve for the bending. So you can expect a question by comparing the first two terms, or the first and the last one, anything like that. So if you compare the first and last, is nothing but T by J is equal to G theta by L. And what we discussed is that torsional rigidity is nothing but to produce a unit twist. That means theta is equal to 1 for a unit length L. So we can say that T is equal to Gj, where Gj is called as the torsional rigidity of the shaft. As the name indicates, it is the resistance offered by the shaft against the deformation in the cross section. So another thing is the torsional strength, which is nothing but the torque per maximum unit shear stress. So if the shear stress is unit, so this will be equal to 1. Then we can rewrite this equation as T is equal to J by R into tau. So this is nothing but the polar section modulus Z. We have discussed in the previous class. So rewriting this equation will give ZP into tau. So in a way we can say that the strength can be compared using the by comparing the polar section modulus also. So that is an alternative way of comparing the strength. Same methodology that we have used for the bending stress also. So there we have used Z as the criteria to measure the strength. Here also the same can be used. So basically when we design a shaft, it's not something like what we did for the bending. Two different criteria has to be considered while designing a shaft, which is subject to torsion. So the first criteria is the strength basis, where the maximum shear stress produced on the outer surface of the material should be within the allowable value. So the tau generated should be less than the tau permissible. So tau permissible is nothing but the one which is on the outer value. So this tau is nothing but the one which is developed with the outside the material. So tau is equal to T into R by J. So this value has to be lesser than the allowable value. So that is the criteria called as the strength criteria. And the second criteria is the rigidity criterion, where the diameter is calculated based on the given value of angle of twisting. So in order to, you can have two conditions, where you will be given, for an example, we can say that they will be asking you to design a shaft so that the maximum shear stress is equal to 50 megapascal. So you are not supposed to design something which is which will develop a shear stress beyond 50. And also they state that the angle of the twist should be less than 2 degrees. This is how they will state. So how will you do that? Obviously you have the all the other values. So if you compare the first two equations, T by J is equal to tau by R. If you use the first equation, we can say that 50 is the value of shear, and R is nothing but D by 2, which is equal to, say torque is equal to 100 into 10 cube Newton mm, divided by J is nothing but 5 D raised to 4 by 32. So when you solve like this equation, we will get a value for D. This is how you get the, or do the design based upon the strength criteria. Now how will you do the same design using the rigidity criteria? For that we will use the first and the last terms, G theta by L. So what we'll do here, so we will apply the same values here. 100 into 10 cube is the torsion value that is given in the question. J is nothing but pi D raised to 4 by 32, and G is something 80 gigapascal, so 80 into 10 cube into theta is given us say some 2 degree, right? So 2 into pi by 180. We have to convert it into degrees. Sorry, radians. So divided by L. L, say L is equal to, given that L is equal to 2 meter, is equal to, so 2 into 10 cube. So the reason why I am adding a 10 cube here is to convert the meter into millimeter. Everything is converted into millimeter. And say the torque is equal to, torque is given as 100 Newton meter. So when you solve this equation, you will get another value of D. So comparing these two values of D, you have to select the maximum value, because if you have a maximum value of D, obviously this stress will be less than 50. Obviously, when you have a higher diameter, the torque, this is a diameter which limits the torque to 2 degrees torsion, or angle of twist to 2 degrees. So if you have a diameter greater than this D, definitely the angle of twist will also will come below 2 degrees. So to use these two criteria, get the value of diameter and select the maximum D. That's how the design is for the shaft is being carried out. Now, if you discuss the torsional failure modes of the shaft, this is very interesting, where you can see two different type of failures here. So you will expect that this is for brittle material and this is for the ductile material, but actually that is not the truth. The reverse is correct here. Basically, ductile materials fail in shear. So ductile materials fail in shear. We know that shear is equal to T by J into R. So when ductile materials fail in shear, I hope you all remember about the pure torsion. We don't have a normal stress here. We have only shear here. So if you take the theta P value, or sorry, ductile materials fail by shear. So if you take the theta S value, I think you all remember the equation, tan 2 theta S is equal to sigma x minus sigma y by 2, this equation. So you don't have a value for sigma x and y. So 2 theta S can be equated to pi, and finally theta S is equal to what? Pi by 2. That means you can expect a failure to happen, or you can expect a shear failure to happen at a plane which is at an angle of 90 degree to the axis. That means if this is your axis, this is the plane, cross-section plane, something like this. So if you look here, this is the plane where you can expect a ductile failure to happen. This is for the ductile material. See, this is the axis. So a plane perpendicular to that got sheared in the ductile failure. But that's not the case for brittle. So when you take the brittle, it fails in tension. So tension means normal stress you have to consider. So for the normal stress, I hope you remember the equation, tan 2 P is equal to 2 tau xy divided by sigma x minus sigma y. Here we don't have a sigma x and y, because we are talking only about pure torsion. So if this value is 0, then 2 theta P is going to be pi by 2, 90 degrees. So theta P is going to be 45 degrees. You simply go behind the values of tan. Or kindly refer to the slides that I have used to explain about the principal stresses and the corresponding planes. So you can get the values of these two, theta S1 and theta P. Okay, 45 degree. That means you can expect a failure to happen at an angle of 45 degree with the longitudinal axis. So if you look here, this is what that particular angle is. This is that angle. So if you look here, you can see an angle of 45 degree with the x-axis. If you look at this particular figure, you can see it's a beautiful figure where you can see this is the axis and you have a shear plane, failure plane at an angle of 45 degree. So don't worry about this fatigue origin or something like that. I have taken this figure from a journal where you can see clearly see how the plane of failure has developed in a material, or how the plane looks like after the failure. So please don't confuse with the conventional system. You have to understand how the material fails, and based upon that you have to conclude the mode of failure. Now the last topic we have to discuss here is the torsion on the composite shaft, because right now we have discussed only about a shaft which is having constant cross section, but here you have the different cross section, along with that you have different values for the torque. So how will you solve such kind of question? So one thing you have to understand that the net value of angle of, not the angle of twist, shear strain is going to be, or this can be equal to This is equal to the summation of TL by J, GJ in each section. That means if you take AB, BC and CD here, we can say that the shear strain is going to be TL by GJ of AB plus TL by GJ of BC plus TL by GJ of CD. This is how we can get the value of net shear strain. Now the question is, what should be the value of T here? So the T of AB will not be the same as that of BC. That will not be the same when we consider the case of CD. So we have to take a sign convention for this. So let us discuss that sign convention. So a right hand thumb rule is applied. The simple sign convention says that when you curl your finger along the direction of the torque, and if the thumb is pointing outward, then that particular torque is considered as positive. So if you look this 80 Newton meter, if you curl your finger along with this torque, the thumb is going to point outward. So this is a positive shear. So sorry, positive torque. This is a negative torque. This is a positive one, and this is again a positive one. And I hope you all remember the principle of superposition, where we take in the equilibrium. In a similar manner, we have to take the equilibrium here. So look here, if you take the AB, you divide it centrally. Here you have an 80 here, so obviously you have the other three values equal to 80. Similarly, if you take BC and if you equate the left hand side and the right hand side, you will end up with a value of 70. And if you divide the CD at the middle portion, and if you take the LHS is equal to RHS, then definitely you can end with 10 Newton. Okay. So definitely this particular 80 is going to twist in one direction, 70 is going to twist in other direction, and 10 may be. So based upon the direction of twist, you have to add or subtract. Doesn't mean that always you have to add. Sometimes based upon the value of torque, you have to subtract. So independently you find the values of the shear strains, and you add everything together, will fetch you the value of the total shear strain. So this is how we design or we solve the problems in the composite shaft. That's all for the session. We will meet with some other topic in the coming sessions. So kindly go through all these explanations. Thank you.